Hello, everyone. I'm very happy to be with you today. So I'm Caroline. I'm one of the co-founders of Dataveyes. And Dataveyes, we are a small studio specialized in human data interactions. That means that our job is to make visible and usable information that is contained in very large volumes of data. So we design and we develop tools or softwares or applications that help people understand data or interact with data or develop new use with data. And so we created Dataveyes with my partners because we were convinced that our brain doesn't work like a computer. And as humans, we need some specific interfaces, like visual interfaces, for example, to understand the complexity inside the data. And that's why at Dataveyes, we are doing a lot of data visualization, like custom-made, tailor-made data visualization, advanced data visualization, like the one you see on the side, which are projects we created during the past years. And so just to finish with the presentation, we are a team of 6 people at Dataveyes with a mix of designers and developers, and we are based in Paris, in France. So today I'm gonna talk about a tool we have been working on since the last month, and it's called Knowl. It's a tool for mapping very large corpus of documents, a very large corpus of knowledge. And it's just a first prototype for the moment you are seeing. It's a first prototype that maps about 50,000 scientific publications about the coronavirus. And with this tool, we have a strong ambition, really strong ambition. We want to revolutionize the way we search for information in large volumes of documents. And so that's the ambition, and that's the talk will be about. And now I'm gonna tell you a bit more about how it goes in real life and how we have been working on this. So what was the trigger? How did we start this passion for search? So well, when the health crisis happened in the spring, we wondered what we could do as a data visualization expert, because we were not at all expert in molecular biology nor in virology, and we didn't know how to produce masks, but we were good at dealing with information overload and data massification, and we discovered that that was a real problem during this crisis. For example, we interviewed Ferdinand, who is a postdoctoral researcher in a research center, and he told us that during this crisis, he was flooded with an avalanche of preprints, papers, and information, and he felt he was stuck by the amount of data. It was impossible for him to digest everything, and he was not used to that, he told us. He feels that it's good that there is transparency about all the research works, but he was really afraid to waste too much time if he has to assess all of this. And in fact, available information about coronaviruses have never been so rich or accessible as it is now, because at the beginning of the crisis, lots of scientific publishers gave free access to their articles about coronavirus to ease the research about the disease, but they also speed up the review and publication process for new articles, and this led to several thousands of new scientific papers being published and released each week during the month of April and May. And this is the biggest explosion of scientific literature ever. So that was the trigger, and now why do we have a problem? Because this practice of open science, it has a huge potential. It's really fascinating, but it also introduces a new challenge, which is discoverability. So having too much content, too much material, we risk missing something important, something we will not find because it's drawn into the mass of information. For example, Ferdinand, he told us that he's often afraid of missing an article that already exists about the subject he's working on. And for him, checking if something already exists or not in the massive amount of already published scientific papers, it's really complicated. It's cost too much time, he told us. And this discoverability problem, it can have very concrete impact. So let's just talk about one. It has already claimed lives during the Ebola crisis in 2013, for example. This is a story told by Bernice Dan, who is the Chief Medical Officer of Liberia's Ministry of Health. So it's in an article published in the New York Times, and she explained that during the 80s, the early 80s, there have been already one scientific work that pointed out that Liberia needs to be included in the area where the Ebola virus was endemic. And this scientific work was already warning for the risk of an epidemic and risk of a pandemic. But this work was published in some European medical journals, which are really more confidential than the English ones. And so it has remained unknown to local health authority in Liberia. And so that's how we had this crisis with the Ebola pandemic in Liberia, which cost some lives in Africa. And so this is a terrible example of what we call dark knowledge. Dark knowledge, this is the part of the scientific knowledge that cannot be found or cannot be reached or cannot be used. So back to our coronavirus examples, among the scientific publication we have been working on for this project, so the publication that have been open and published during the crisis, we estimate that 50% have never been quoted nor mentioned by any other scientific work. And we've also discovered that at least 6% of this publication are not in English, but in Chinese or Korean or Arabic, Russian. So those publications which are not in English, they will probably never be found by any American researcher or any European researcher if it's not the same language. And that's always a problem if a research work cannot be found, because maybe this work was bringing something new and very useful for other researchers, but also if several researchers are working at the same time on the same subject without knowing it, but it's miss of time. They would have been able to save some precious time if they were aware. And so at the end, why do we have this discoverability problem? Let's look at what are our tools today to deal with this discoverability problem. Most part of the time, researchers are using search engines like PubMed or Scopus, but also Google Scholar, or Microsoft Academic when they need to look for scientific papers. And according to us, but not only us, other researchers have this opinion, those search engines are not always the best way to tackle with this discoverability problem. First, for user experience reason, because conventionally the presentation of a search result, it's a list paginated, like the one you see here from Google Scholar. But let me ask, how many of you are looking at the result located on the third page of results? Only the third page. I guess not many people. And most part of the time, there are hundreds and hundreds of pages of results. So that's a lot of articles that you won't be able to find. Second reason, it's transparency reason. There are arbitrariness in the way Google or Google Scholar work, but other search engines also, because the ranking algorithm is not transparent. We know, for example, few things, and we already know that there are some bias. For example, publications that are in English language, they are more likely to be on the top of the list than other language, but also publications that have been published in really well-known reviews or publications that are already cited by a lot of articles, they are more likely to have a good rank and more likely to be found. So which is really good when you are looking for some conventional definition of a subject, or when you are looking for the common sense, what most people are thinking about the subject. But maybe that's not the best way to take a critical look at the subject, or to have a deep understanding of a subject, or to find some raw material for your scientific study. So maybe we need to admit that the most efficient search engine in your day-to-day life, when you need to find a recipe or the title of a movie or something like that, it's not the best tool for searching for scientific information. And the last reason I wanted to point out is search engine, they are not always good, and in particular, they're not good when you don't know how to describe what you are looking for. Because maybe you don't know how to name it, or maybe you don't know what it looks like, what you are looking for, or maybe you don't even know what you are looking for. So for example, imagine if you read a very interesting article about your research subject, if you're a researcher, and you would like to find some similar publications, but that have been published several years ago in the past. Or imagine if you would like to know if some other work is refuting this article that you find interesting. Or imagine if you want to find some other works that are using the same experimental procedure as this interesting article, but for other disease, for example. Well, if you are in this situation, I wish you good luck to find something with Google or Google Scholar. So, in our opinion, the user experience is key in this solution. So, of course, there have been some innovation in the field of information research during the last years, like, for example, faceted filters or similar content recommendation, personalized recommendation or automatic classification, NLP or entity recognition and metadata enrichment. But all this is great and it does help, but it's still not enough in our opinion, because most part of the time it's still designed as black boxes, like magic recommendations. It's still designed to give you a quick answer rather than giving you more exploration capacity. So the design choice of search engines, it's often to limit what you can access easily. And we think it's not the best way to empower a user when they're looking for some scientific publication. And according to us, it's not a recommendation problem. To deal with this discoverability crisis, it's not about improving how artificial intelligence algorithm will give you the best 3 results ever. Because we have to admit that 3 results is not enough when you are looking for publications in your scientific field. So according to us, the solution is more about improving the experience to give people access to much more information than before, and to give people the right tools to be able to navigate inside these very huge amounts of information, but to make them able to find by themselves relevant contents. And according to us, that's the real challenge. And so how did we work on this? So let's share some few elements of our methodology. So first, we always work with real data. And in this case, for this prototype, we are working with 2 data sets. The first one is Lens COVID-19 datasets. Lens, it's an academic search engine provided by an independent non-profit organization. They have selected several thousand of articles and patents about coronavirus. The second dataset is CORD-19. It's the COVID-19 open research datasets, which contain more than 200,000 scholarly articles, and it has been created by the Allen Institute for Artificial Intelligence. So those are the 2 datasets we are working on. We are doing a lot of user research. We are supporting our experiments with interviews and user testing with a small group of experts or researchers. We are mixing the different skills in our team all the time. For example, designers, developers, statisticians, we are all working together all the time on the same problems. And also, we prototype to solve problem. So rather than specifying a solution to test, we prefer to describe problem, and each member in the team is in charge to find solution to try and to test. And so in this project, the problems we wanted to solve were how to do something that is good where classic search engines are not. So for example, how to allow users to better understand a corpus as a whole, or how to help users navigate in very large volumes of content, or how to help users find something that they cannot describe, they don't know how to describe, or how to reduce the fear of missing out on something important. And we have a strong intuition that mapping can be an important part of the solution. In fact, it was Google Map rather than Google Search. So we were interested in the appearance of Google Maps and how this technology has changed the use. So we read this book, which is really interesting, which is called Never Lost Again by Bill Kilday. And there was this citation that was inspiring for us that said, "No one after us, no generation to come will ever be lost in the way that every generation before was." So our approach was first to try to map the publication to give an overview of the corpus, to bring a physical dimension in. Because in data visualization, specialization of the information brings a tangible and physical dimension to data, and it plays a very positive role in the ability of people to appropriate data and to play with data. And this is something we have observed since a long time in our profession. So it helps people, specialization of information, it helps people get a mental picture of the data. It also helps people interact with the data because they feel more able to get their hands on, because this physical dimension, it brings, it breaks the black box effect. And also specializations, it also fosters memorization. And all the theories about the mental palace are based on this observation. So armed with this conviction of mapping can be a solution, we wanted to try to what extent this specialization, this localization could help to better search in scientific publication. So first, we have been looking for the best layout to map the dataset. So we wanted to find how to get each publication with a specific location in the map. So try to visualize this corpus. So we produce a lot of experiments about how to position the publication in the physical space. It's a bit like if we have, the dataset was like a ball of clay, and we try to mold the clay to give it a shape according to specific part of the dataset. So at the end of all this tested, and this is really a sample of everything that we tested, at the end we kept two approaches. The first one was a citation network graph. So the first approach, it's a graph of the citations link. It's a network graph. That means it's built with a force-directed layout. So how does it work? Each node here is a publication. And the publication, they are linked together when they are citing each other. So each time a publication is citing another work, we have those links. And we use a physical simulation where the links act as attractors. It's a bit like if we have some balls that are linked together by stretched rubber bands. And as you let go, all the rubber bands try to bring the balls together, and the systems stabilize in a way that optimizes the expression of each link. So it gives an idea of the organization, the structure of the corpus according to the citations link. And we know that citations links, they are very important in scientific research because science is made by iteration and progressive refutation. So we were really interested in finding a way to make this, to make visible this iterative nature of science, to show the making of science thanks to the citation links. And also, with this graph, we were able to make visible this dark knowledge in the dataset. So I don't know if you have seen it well, but let me, I don't know if you see the corolla here at the periphery of the graph. So this corolla is made of all the articles that are not linked to others. So the 50% of publications that are not cited by anyone else. So in this map, they are still here. We have this corolla, which is the dark knowledge that usually you don't see, and here it's here at the border. It remains visible in this map. The second experiment, the second way to map this corpus, it's a dimension reduction map. So here, it's really here where we used machine learning. And here we have another way to organize the datasets. We reduce each publication to a metadata sequence. So it's like a unique sequence of keywords and information that reflects each publication. So we use 26,000 different keywords to describe the publications, and each publication can be summarized by a sequence of 1 and 0, describing if each keyword belongs or not to the publication. And after that, we have, so this gives us vectors in 26,000 dimensions. It's like coordinates in a multidimensional space with 26,000 dimensions. And then we use a machine learning algorithm, which is called UMAP, to switch position from this multidimensional space into a 3D or 2D space. So we use UMAP. It's an algorithm in the same family as t-SNE, but it's better than t-SNE for our goal. And this kind of algorithm translates proximity notion in a multidimensional space into proximity into a three-dimensional space in a way that articles that are close to each other in the 26,000 dimension space are still close to each other in the two-dimensional space. And articles that were far away in the multidimensional space are still far away in the 2D space. So it's a way to translate 26,000 dimension into 2 dimension while preserving the topology. And so at the end, articles which have the closest sequences of keywords are close to each other in the map. So here the idea was to replicate the physical experience that you have when you are in the library and you walk around the different shelves and you find a book that is interesting for you, and step by step, close to each other, you look at other books, and you will find something that you are not really looking for. So we had these 2 ways to draw the map of the corpus. And they were both interesting, and so we made some user tests to determine which one was the most easy to use and to understand. And at the end, the dimension map, the dimension reduction map, was really better understood without any doubt. It was really clear. Testers felt more comfortable with this map. They interacted with it more naturally than with the citation graph. And also, testers told us that it was easier to understand, it makes more sense for them. So we have seen here the potential of machine learning for our work at that moment, where we achieve a better organization, a better localization, thanks to machine learning. So let's talk about another point, but just let me find, right. Just 1 minute, I'm short of battery. Right. Okay, sorry about that. My plug was not working anymore, but I'm okay now. So something else I wanted to tell you about, it's the colors, because it's important too here. If you see the 2 maps, the one at the left and the one at the right, there is a huge difference in your ability to perceive space and to find some location. So we need to have some colors that are relevant, and here colors are reflecting clusters. So to get these clusters, we also use a machine learning algorithm. We use an algorithm that is called HDB scan. It's a hierarchical clustering algorithm. That means that we are able to find some parent cluster and children cluster inside. And it's a clustering by density. That means that we can identify some clusters even in complex shapes in the map. And to find those clusters, we tried different implementation of this algorithm. So HDB scan was better than a usual clustering algorithm like K-means in its ability to detect complex shapes. But you can detect those complex shape in 2 dimensions, but also in 3 dimensions, 4 dimensions, and any of the different space we can create with this 26,000 dimension we add. So we made some different tried, different tested, and at the end, we found that implementing the clustering algorithm in a 10-dimensional space was give us the best result. Just a small point again about the color. First, it shows you the different clusters, but also it can show you some other dimension. For example, for example, here we can use the color to display, to show the number of citations. So we can change dynamically the color of the publication, and here you have some other patterns that appears. And for example, we are able to see that the cluster talking about coronavirus in biology and virology is the most cited in this corpus. And just let me give you a few explanation about the labels. So the labels, we also find them using some data treatments, and here we try to find the most used keywords to describe the cluster. So for example, we found the keywords that are most frequent in the cluster and not in the rest of the corpus, in comparison with the rest of the corpus. So let's finish with the rest of the interface, because this map is not working alone. There are some user interface elements to form a tool and give users some features to explore further. So we have, like in Google Maps, the ability to zoom in, zoom out, or to pan, or to hover any article and see its link. But we have also the ability to use some filters. So for example, it's really basic because it's just a prototype and we have been focusing more on the map. But so you can add some filters for the year or for the field of study or the keywords. And when hovering a filter, you see directly which part of the map is concerned. And so you can create this filtered version of the map according to what's important for you. And you can also display the list of all the publication. And you have this correspondence between the map and the list. You can investigate further on one article. So you can select an article and you can see its metadata and the abstract and everything we have for this article. But also you can explore the citations, so papers which are citing this paper or references, the bibliography. And we can, for example, display the list of all the citing papers and see where they are on the map, if they are from different fields of study or if they are from the same fields of study. So this is really useful. And also we can display a list of similar publications. So if you find something that looks good for you, we can automatically find the closest one and display the closest one. So this is the first prototype we have been working on, and voluntarily we have not put any search box yet. So this is really because we wanted to keep this for later. We wanted first to explore the potential of the map and the complementarity between the search options like filters and things like that and the map. And so the questions we ask ourselves is, how does it fit together, this map with the user experience of a classic map like Google Maps and the more classic user experience element like the filters and the list. And we have done user testing on that, and the user tests show that users still use the map relatively little as an exploration medium, but more as a feedback, as a way to evaluate the results of their search, as a way to see if the filters they're using, is it relevant for them or not, or how many results they will get or not. But for the moment, the map is not really the first way to interact and to look for something. So this is interesting, but we would like to investigate how we can make the most out of this map for the searching capacity. And so We have still a long way to go, still progress to make to succeed in this challenge of improving the research experience in scientific publication. But this is just a first step. The next step, we would like to try to visualize relations between entities extracted from the publication. So not anymore mapping the publication and the relation between articles, but mapping the relation between entities, relation between what articles are talking about. For example, we can extract disease or molecules or viruses, part of the body, gene, and so on. And all these entities are discussed inside publication. So if you read 1, 2, or 3 publications, you will see the relation between those entities. For example, you will see that an article is making a relation between a virus and a part of the body, and a virus and a gene. But you cannot do this for thousands and thousands of publications. But by automatic extraction and by visualization, spatialization, we can make appears the relations between entities for the whole corpus. And maybe we will make some correlation appear that you will not have seen other way, because this is what you can do when you can visualize such a massive amount of relations. So I hope, so this will be our next prototype. We are working on it at the moment, and I really hope I will be able to share it with you soon and to give you some more feedbacks about this mapping capacity to improve the way we search. So this, this is the end. This is the story of what we have been working on since the beginning of this crisis. And I'm really curious of your question now. So I'm going to have a look at the chat.
Hi Caroline, it's James here. Can you hear me okay?
Yes, I can hear you.
Cool. Sorry I was late at the start. There was a previous session that overran. So yeah, if people can send in questions, I don't know whether you can see there are some questions already in the chat box that have been coming through. I can see some people are typing as well. Yeah.
All right. I don't know if I go over the question by order of if.
I can work backwards if that's helpful and read out the questions.
All right.
So question, did you experiment with modularity-based clustering methods? How did you validate or test the clusters with users?
All right. We tried different algorithms, but we really wanted to have a hierarchical clustering algorithm, and so we tried several and we tested them with users, and the most important thing was how people feel they can find something in the map. So we were showing the map to testers, and if they feel they were lost and if they feel it was like a mess, we were not keeping the algorithm.
Great, thanks. Another question, how did you test the layout algorithm to arrive at the dimensionality reduction method was better?
Yeah, it's the same thing. First we see what's the result when we map the publication. So what's the result of the algorithm? Does it bring something better in terms of specialization, in terms of capacity to have your publication that are not all at the same in the same ball at the center, but that are positioned differently in the space. So mostly the idea was to find the best algorithm to create some space with more publication and some space with the less, and to see those clusters appears. So the capacity of making clusters appear was a very important point in our evaluation of the different algorithm we tried. And after that, when we feel it was good, we show it to our testers and we ask some feedbacks and we give testers some basic task of finding publication inside the map or describing the map, and we see which one was more efficient.
Great, thanks. Another question, you mentioned that users are less likely to explore using this map. How have you attempted to enable this exploration?
Sorry, I missed the users are more likely to?
So you mentioned that users are less likely to explore using this map. So I think the question is around what plans do you have for developing exploration functionality, tools, capabilities?
Yeah, our idea is really to have an interface that makes some rebounds between classic filtering and searching options and the map. Like if all the interface was reacting at the same time when you perform some action. So, for example, if you zoom somewhere in the map, it should update at the same time the filters on the list. And if you feel one filter is interesting for you, it should show directly how part of the map you will lost. Or if you get interested by, for example, one article, you should be able to see at the same time. You should be able to read at the same time the abstract and see what's the impact of this article on the rest of the scientific field, for example. So the idea is giving you more options to go from one article to another, to go from one ID to another, to go from one keyword to another, because it's really complicated to know which one is the good keyword for you. And this is something that is really common in the interviews we made, is that at the beginning, people are naming things differently. And according to the location, people are describing things differently in the publication. So if you have to rely only on 1, 2, 3 keywords, you're really, there is really a risk that you miss something. And that's exactly the fear of researchers who are working on a specific subject. It's the fear of missing out some work that have been already published and that they don't find because they don't know what is the correct keyword to find that. And this is why any option to interact with this corpus of document that doesn't ask you to describe something with words, but by proximity, by going from one to another, clicking here to see what's the result, it's good.
Perfect. Thanks, Caroline. That was a really fantastic, really interesting talk. Hopefully you've had a look at some of the compliments in the chat channel. I think a lot of people enjoyed that and found it really interesting. I'd ask if anyone has any questions, further questions for Caroline, just post in the leaders Slack chat, and hopefully she'll be around to pick that up. So now we're moving on to the US time zone coverage. So we have the welcome address for the US part of the conference. So I would direct people over to there, and we'll get started with handing over the virtual baton. Thanks very much, all. Thanks, Caroline.
Thank you, everyone. I remain available in the Slack channel, so do not hesitate to ask your question. Yeah, great. Thank you very much.